All right, hello there, Earth Science students. Welcome to our day where we're going to be reviewing what we learned about um, plate tectonics on day 10, and then moving forward and pretty much covering the rest of chapter 4 in our book. Now, just to review from the last time that we actually met, we were learning about two important vocabulary terms. We learned that there were one way to divide the upper, few hundred miles of the Earth's, of the Earth itself up. It would be to describe it as being either part of the lithosphere or being part of the asthenosphere rather. And remember, the main difference here was we were sorting out layers based on their mechanical properties. The lithosphere was the crust and the uppermost and coolest parts of the mantle that make a strong, brittle outer layer called the lithosphere, whereas the asthenosphere was the hotter, weaker region underneath the mantle that is still solid, but can move. Think of it as being like maybe a very firm clay or something like that. It's hot, it's slightly molten. It's not actually, though, like flowing like a liquid the way you're thinking of lava or something like that. So the lithosphere, you might recall, was about 100 kilometers deep, but that's about 60 miles over underneath the oceans. And the asthenosphere then went below that, basically as far down as you want to go. I mean, it's just going to get runnier and runnier the farther down you go. But the upper asthenosphere, the temperatures get close to melting, but not enough. So technically it is a solid, but it's a solid that can move, that can flow slightly, and so on. And remember, we actually even highlighted this exact sentence in the book, and I think it bears remembering again, where we said that although the rock in the asthenosphere is largely solid, it responds to any forces acting on it by flowing. In contrast, the relatively cold and rigid lithosphere responds to forces by bending or breaking. So we have this very strong, brittle, hard outer layer to the Earth, the lithosphere, with a firm but movable below it a layer that is the asthenosphere. And remember, we have this important way again to sort out the difference here. We're talking about two different mechanical properties here. If you put stress, like plates are trying to move, lithosphere tends to bend or break or fold, whereas the asthenosphere is going to flow. Admittedly, very slowly, on the order of a few inches per year, but it will flow. That's in contrast, though, to the way we talked about the Earth when we're going to be saying about things like crust, mantle, and core. Those are different chemical properties. The crust is mostly made of silicates, things like that. The core is going to have lots of heavy metals and so on. They have different chemical properties. We talked last time we met about how the lithosphere is broken into plates. There's no magic here. It's hard and it broke. It was a thin, hard shell on the more squishy inside of the Earth, and it broke. And most of it is in the form of 7 major plates. And then, these plates can move, and we're going to find out today why they move and so on. But as they move, well, that doesn't end up meaning all that much for what's on the middle of the plate. It's just kind of riding along. But at the boundaries, that's where the action is going to be happening, where plates are going to have to slide past each other or go under each other or whatever. That's where things like earthquakes and volcanoes and mountain building is all going to be happening. Now, last time we met, we talked about the fact that there were going to be 3 different kinds of plate boundaries. There were going to be the divergent plate boundaries. That's the one we actually spent time on the last day of the class, where we talk about plates moving apart, particularly in the case of ocean plates, we talked about seafloor spreading. Today we're going to be talking about convergent and transform boundaries, but just to review, last time when we were talking about those divergent boundaries, well, most of them are under the ocean. They're places where 2 adjacent plates are moving away from each other, typically under the ocean. And magma underneath there just rises up to fill in the space in between. So as these plates are spreading out, we are getting, more fresh magma welling up in between, creating new crust. We had a number of different words for this, like constructive boundary and stuff like that, but really the term I want you to latch onto is seafloor spreading. Okay, that's going to be the term that most often appears in the book and so on when we're talking about this process here. Along those seams between those boundaries, where the plates are spreading out and so on, you get these mid-ocean ridges. And remember that these are high. They're at least a couple kilometers higher than the surrounding ocean basin. It is in fact the largest feature on the surface of the Earth to have this, tens of thousands of mile long band of mountains under the ocean. And the reason why it is higher is actually kind of astonishing. It's nothing more than the fact that it's fresher and hotter. And those rocks are hotter and they have, by thermal expansion, they're bigger, they have expanded. And so they poke up higher from the ocean floor, higher from the center of the earth than the cooler rock around them. Nothing more than they've expanded. And remember, as they get older, they get pushed farther away from the axis, to use the right word, of the ocean ridge. They get cooler, and therefore they are shrinking. As they cool, they contract, and so the ridge gets shorter and shorter and shorter, less and less high above the ocean floor as you get further away from the mid-ocean ridge. And that seems astonishing, but keep in mind it does take about 80 million years to cool down those rocks that are in the mid-ocean ridge. They have plenty of time. By the time it cools to the same temperature as the rocks around it, it may be a few hundred miles from the mid-ocean ridge itself. We normally talk about this kind of divergent boundary happening in the ocean in the form of seafloor spreading, but we also talked about examples of continental rifting, where continents are being torn apart by the same kind of process. And the one that we spent the most time on was East Africa, where Somalia and parts of Kenya and so on are being torn off of the rest of the African continent. They're simply just processes at work that are pulling the African continent in two different ways, and it is currently being rifted in East Africa. A similar process happened about 20 million years ago that opened up the Red Sea as Saudi Arabia broke off of Africa. We talked about the fact that like a billion years ago, the same sort of thing happened in North America, although it failed to completely rift, but that's why there are these igneous rock formations in places you aren't expecting, like Iowa. For that matter, it's part of the story of why you probably know that there's earthquake faults in the Wabash Valley and in New Madrid and so on, and we'll talk more about that in a few days. But that's part of another example of a place where the North American continent tried to rift apart but failed. Well, today we're going to keep talking about these different kinds of plate boundaries, what can happen along them, and ultimately why they are moving the way they do. So today we're going to work through our second and third of these different plate boundaries. And the first, the one that we're going to spend time on, is the convergent plate boundaries and the subduction that happens along them. This comes from section 4.5 in your book. I always like to throw out these objectives here to make sure you remember that we want to be able to, the book says we should be able to compare and contrast 3 different kinds of convergent plate boundaries. Hey, let's make sure we're clear about that. We have 3 different kinds of, let's back up for a second here. We had 3 different kinds of boundaries right here. We're making sure we can do all of them. But here's the deal. That one that says convergent, the red one in the middle, there are 3 different kinds of those. We'll see in just a little bit. And you're going to be able to name an example of each of them. All right. EVSC's list here, we're going to be looking for words like convergent boundary, transform boundary, convergent collision, trenches, rifts, volcanic island arcs, things like that. You can always, I will draw your attention though to, let me just bring the pen here for a second. I will draw your attention here to a term I should have highlighted, Harry Hess. Okay, we'll talk about him in just a few minutes, but Harry Hess is another guy who, along with Alfred Wegener, that we should be talking about as we go along. All right, so today we're going to first start off by talking about the convergent plate boundaries, these places where 2 plates are moving toward each other and something's got to give. All right, well, if 2 plates are going to be happening where 2 plates are moving toward each other, and the leading edge of one is just going to have, one's got to go under the other one. And so one of the plates is going to be bent downward. It has to slide underneath the other. And okay, even in like a grade school textbook, they're going to have a diagram similar to the one I have shown up here, except actually there's a whole lot of detail going on in this diagram that bears some time talking about. Okay, the first thing I want to mention here is this idea of subduction zones. What's going on here when there is subducting of oceanic lithosphere? Well, old ocean lithosphere, old meaning it's far from where it's being created along the divergent plate boundaries of like the mid-ocean ridges. So this is maybe, 150, 180 billion years old or something like that, is a little more dense than the asthenosphere. By cooling, it has become more dense, and it is starting to sink. It's easy to make this lithospheric plate take a dive down into the asthenosphere because it's a little heavier than the asthenosphere. It will want to sink right there. In contrast, this continental plate, made up of granitic rocks and so on, is generally going to be lighter than the asthenosphere. It's going to want to stay up on top of it. All right. Along with where the oceanic lithosphere is diving down, under the continental crust, you'll see that there's typically a trench that occurs in the ocean, a place where it's a few kilometers deeper than the surrounding seafloor, as that ocean floor starts to subduct down under. And again, we'll see some examples in just a few minutes. I'm going to give you a tour of some such places in Google Earth. All right, so you expect to find a trench there when there is oceanic plate converging with a continental plate. The angle at which this happens, where the ocean starts to take this dive here, actually varies quite a lot. It depends on how cold and dense this ocean plate is getting. It can actually take a dive almost at a 90-degree angle. It can be very, very shallow and so on. All right. So it just depends a lot on like the relative density of this part of the oceanic lithosphere with the asthenosphere in that same area compared to the density of the continental crust. That is not an easy thing to generalize. They vary quite a lot from one to another. Now, these convergent plate boundaries, the ones that we happen to have shown you so far were oceanic plate converging with a continental plate, but there's other combinations too, like oceanic plates converging or continental plates converging. Well, I want to spend some more time on this one first, this idea of these one oceanic plate converging with one continental plate. So we are going to work with these little kind of cartoons here that are going to show us oceanic versus continental convergence, oceanic versus oceanic, and continental versus continental. But let's go to this first one first. Oceanic plates converging with continental plates. Oceanic continental convergence being the technical term here. So this is literally the exact same figure I've been showing you all along here so far. But this is going to happen when you get a plate that's capped with continental crust colliding with a plate that's capped with oceanic crust. And the oceanic one is just going to be a whole lot more dense than this continental crust. In general, the continental crusts are made of granitic rocks, which are relatively light compared to the basaltic rocks of the ocean. But just also the ocean, by its cooling, the ocean crusts are going to be denser. So in general, when they collide, the oceanic crust is going to dive under the continental crust. And then things get really strange. As this subducting oceanic lithosphere starts to dive down back toward the mantle, when it hits about 100 kilometers down, or about 60 miles, roughly where I've labeled with this yellow line on here, something strange starts to happen. There starts to get to be melting. Now, it isn't where you think, though. You might think that it was this ocean plate, as it's sinking, it's getting warmer and warmer. You would, as it gets down toward the mantle, it's going to start melting. Maybe there are some minerals in there that are melting, but that's actually not what we're talking about. This melting is actually triggered in the asthenosphere. The asthenosphere being like what the plate is subducting through. So as this oceanic lithosphere takes a dive into the asthenosphere, parts of the asthenosphere that are touching it start to melt. That should seem really strange. I mean, nothing seems to have changed in the asthenosphere except the lithosphere is passing through it. But actually, it's kind of an interesting and important change that's happening in the asthenosphere as this oceanic lithosphere passes through it. So let me illustrate what's going on here. I'm going to zoom in a little bit closer just to make it more clear. So here's this plate of subducting oceanic lithosphere. It's colder, it's more dense, and so it's sinking. I don't think we have a hard time picturing that. It's thicker, it's denser, it's going to want to sink down through that lithosphere. Not fast, we're talking a few inches a year, but it's going to sink. But another property that it has is that it is saturated with water. This oceanic plate here had oceans sitting on it for 180 million years. Any place where water could be trapped in the rocks, it is. And so we are not just transporting minerals and rocks down into the asthenosphere, we're also transporting water. And that turns out to be important because, admittedly, remember, part of the definition of the asthenosphere was it was a place that was too cool to melt. So it was solid. It's hot, but not quite hot enough to melt. So the asthenosphere is a solid, or at least kind of a squishy solid, like Play-Doh or something like that. But when you add water to this material in the asthenosphere, it changes its melting point. That's interesting. Your book draws an analogy that is not exactly right, but actually is pretty helpful right here, where they said, think about it this way. How about when your driveway is icy and you sprinkle salt on it? Okay, you go out after an ice storm or something, you put salt on there. what is the salt doing? The salt changes the chemistry of the water in such a way that it lowers the melting point. So if the melting point of your water was 32 and it only was 20 degrees outside, your driveway didn't melt and the ice stayed. You apply the rock salt to your driveway, it changes the melting point to maybe 15 degrees Celsius. Well, now you are warmer than the melting point and the water melts off. Well, the chemistry is not exactly the same, but it makes a good analogy as to what happens when you add water to the rocks of the asthenosphere. It changes the chemistry of that magma to such that it now those rocks so that now they melt. And so even though doesn't change the temperature of the rocks in the asthenosphere, they've gone from being a solid, albeit a rather squishy solid, to being more of a liquid. And as a consequence, you get these really cool looking little plumes of hot melted asthenosphere that start rising. Now, this is not happening fast, but those little plumes will work their way up. They're lighter, they're less dense than the surrounding asthenosphere and ultimately the lithosphere around them. And they will start working their way, effectively burning their way through up toward the surface as they work their way up over the course of literally millions of years. These little, think of them as little magma chambers or something like that, start working their way up towards the surface. I think that's a really cool and illustrating, illuminating diagram that they provide here. So we just get this melting of this asthenosphere that starts working its way up as these little bubbles, if you will. I mean, they're big. They're the size of a mountain. These boluses of magma that are working their way up, and they work their way up toward the surface over long periods of time. That's really cool, and there are lots of really good examples of that in the Earth to look at as for learning. I'm going to now switch over here to Google Earth, and I'm going to show you some examples from Mount Hood, Mount St. Helens, and west of South America. I will mention when I pre-recorded this next part using Google Earth, I did misspeak. I said that I thought this Mount Hood and Mount St. Helens, which are in the northwest United States, I said it was the Nazca plate that the North American plate was colliding against, but that's not right. It's the Juan de Fuca plate. But that's okay. I mean, the plates that were colliding wouldn't be on the test or anything like that. All right, so if I switch over here, I'm going to try to play this video here and see real quick here. Where's the player? All right, hold on. How do I get that out of here? I'm going to turn this off. I think that does it. No. Sorry. How do I play this video here? If I want to turn this off. What if I just went? No, shoot. Hold on. How do I make this play? Shoot. Alright, so let me go ahead and try to show you some examples of the kind of features that are created as an ocean plate is subducted under a continental plate. And one of the features I wanted to show you was Mount Hood in Oregon. Oops, right here. Mount Hood. Alright, so I'm on my slowest computer that doesn't have such a great graphics accelerator, so the graphics aren't going to be as smooth as I was hoping on I made this. But, alright, let's see here. Whoa, what's going on here? There we go. Alright, so here's Mount Hood. Let me back out a little bit. Alright, so Mount Hood is a volcanic mountain. Let's see here if I can make this a little better. You can see he's out there. He's in Oregon, kind of out in the Cascades, but he's a lot taller than the surrounding hills because he's this big volcano, has a big plume, has come up through the asthenosphere and up through the lithosphere, and is now, I don't know how active off the top of my head Mount Hood is. Let me see if I can get him to animate here a little bit. Let's drop this here. But anyway, so I'm not an expert on Mount Hood by any means, but anyway, it's obviously much taller than the mountains around it. Clearly, a different mountain building process was building this than the things that are in its neighborhood. And actually, let's see if we can have it to see anybody in its neighborhood. I'm going to try to make it orbit here again. Hold on, let's go into orbit around the mountain. It's just not going to do it quite right for me. Anyway. There are several such mountains that are volcanic in origin in the Cascades. In fact, one is certainly far more famous than the others. So let's go to see Mount St. Helens. Mount St. Helens. All right. Again, I wish I was on the computer with faster graphics card. But anyway, all right, so obviously you guys know a little bit about Mount St. Helens, right? 1980, basically the whole side of the mountain just blew out. Giant volcano, big eruptive event in 1980 or something like that. Let's see if we can get a little bit better of a view. Let's see, how can I make him? There he goes. So you can see exactly how he erupted out the side here. But again, this is just another plume of magma that was working its way up after the Pacific Plate, actually it's the Nazca Plate, I believe, was subducting under the Cascade Mountains, and then a large plume of magma formed off that plate as it was subducting, and then rose up through the lithosphere to create Mount St. Helens. And what I want you to notice about where Mount St. Helens, let's see here. Let's see if I can get it to turn here. All right, so now we're looking north from Mount St. Helens, and where are we here? I can't see what I'm looking for. So in the neighborhood, there it is, behind this little piece right here. Look at this guy way over here in the distance here. Let's go over to him. That is one big mountain, right? That is a big volcanic mountain. Come on down here, buddy. I tell you what, this little computer just does not have very good. Let's just do it this way. The 3D graphics on this little computer are not so hot. Anyway, alright. Hey, here's another big volcanic looking thing. Let's switch him back to 3D view, and I think you're probably familiar. This is Mount Rainier. Mount Rainier is this giant, look how much taller this is in the mountains in the area. This giant volcanic peak in the Cascades. Again, very similar processes to what we were talking about, as part of the Nazca, or is this Juan de Fuca? I'd have to admit, we'd have to go look at the exactly which plate is subducting over here. But again, clearly a very large mountain, far higher than the others as this big plume of lava was coming up. Now, again, because I'm kind of on the crappier computer here, I want to show you something that's in the neighborhood, by the way, of Mount Rainier. Let me switch this so that it's got north to the top, just so you're a little more oriented. So here's Mount Rainier. And if we just sort of go down, so we come down the slopes of it and through these fields and stuff. I'll back up just a little bit here. I don't know how familiar you are with the geography of that area, but just downstream from Mount Rainier is, of all things, the Seattle metropolitan area. It's only a matter of miles away. Let's see if I can get all the way zoomed into Seattle here. Let's see, there we go. Getting some better control. All right, let's switch this to 3D view. And what you're going to see here is downtown Seattle. Well, I was going to say you can see Mount Rainier from there. Odds are, actually, most days you cannot see Mount Rainier from downtown Seattle, but not because it's too far. It has to do with the weather conditions there. It's going to let me pivot now. Let's see here. Yeah. There we go. Here's downtown Seattle, and look in the distance. There's Mount Rainier. In a big pyroclastic flow from that volcano, Seattle would be in a lot of trouble. And so, farther, actually closer to the mountain rather, is Tacoma, Washington, and similar such places. So there's a lot of danger, a lot of people in danger from that particular volcano. Kind of a crazy place to have built a major city, but we'll see crazier over the course of the volcanoes material in the course. Excuse me, I had to get a drink of water there. I also wanted to show you one more thing while I had Google Earth up. Let's go to, we'll just use Peru as our search. And let me get this out of the way here. Yeah, I should have done this on the faster laptop. Okay, so this is the web app version of Google Earth, and it does not do the underwater stuff very well. But you can see how there's this big trench here. Now, this is definitely the Pacific Plate subducting under the South American Plate. And, of course, you know that these are the Andes Mountains coming right along the edge here. So the Pacific Plate is being pulled under the South American Plate. You'll learn about slab pull in just a few minutes in the lecture. This is a really good example of a slab pull pulling this plate underneath here. And then you get these volcanic mountains. A lot of the mountains in the Andes are volcanic. All right, well, that's all I wanted to show you for this part, and then we're going to go back to the PowerPoint now. All right, well, that's all I wanted to show you on that one there. Let me switch back over here to the marker. And there it is. Okay. I did misspeak as I was watching that video with you. I realized I did misspeak too. That is the Nazca Plate that's getting pulled under South America, and it is Juan de Fuca Plate that is being pulled under North America. But that's okay. I mean, again, the trivia of the name that's more of a trivia question than than learning. I mean, I'm more interested in the process than the names of the plates or something like that. Okay, so all that so far has been where an oceanic plate was converging with a continental plate. Let's look at the possibility of oceanic plates converging with another oceanic plate. And so like they use this as their example here, where like there's some oceanic crust here converging, and with a second oceanic plate that is converging, if one has to subduct under the other here. And basically the processes are going to be very, very similar here. It's going to work very similar to the oceanic continental convergence boundaries. Once again, we'll get some kind of trench and such. But I do want to, once again show you that again, as this oceanic lithosphere descends, we're going to get melting in the asthenosphere as that saturated oceanic lithosphere brings water down into the asthenosphere, starts triggering melting happening in the asthenosphere, and then plumes of volcanic magma work their way up toward the surface as that happens, creating these arcs of islands here. In fact, volcanic island arc or island arc is an important term here. You might remember I showed you that on the vocabulary list from EVSC there was a gentleman's name, Harry Hess. He was one of the guys who took Alfred Wegener's ideas about continental drift and turned them into the modern ideas of plate tectonics. Remember, Wegener had really good ideas, but he didn't really understand the processes by which this would happen very well, simply because he didn't know anything about what was happening under the ocean and so on. Hess is the guy who discovered, or really did a great job of bringing this all together and making the modern idea of plate tectonics out of that. And he was studying these volcanic island arcs that happen, especially out here. Like one in particular that we're going to spend some time on now is the Aleutian Islands here. If we kind of zoom in a little bit more. If you don't remember your geography or whatever, this arc of islands that comes off the coast of Alaska. These are the Aleutian Islands, and they're part of the boundary. If we switch back to our map of the the plate boundaries, they're part of the boundary between the Pacific Plate and what is actually part of the North American Plate to the north here, but it's all oceanic crust that's up here. So this would count as like an oceanic boundary, even though North America is also on this plate. This part where they're interacting is oceanic crust, so it's okay. We can talk about them as being an oceanic boundary. But I'm going to actually switch to another Google Earth video to show you, again, these are the Aleutian Islands, and we're going to see, well, you can kind of see quite well here, actually, how there's a trench forming. So as Pacific Plate is being transported this way, it's being subducted under the North American Plate here, and we're going to get this ridge of these islands, this arc, this volcanic island arc that Harry Hess would have been studying in just a few minutes. But let me go ahead and see if I can make more smoothly here a transition over here to this video. Okay, so a good example here of these kind of oceanic to oceanic plate convergence boundaries happens. Your textbook uses the example of the Aleutians. This is the north of the Aleutians here. That's actually part of the North American Plate. But the boundary is completely happening with the oceanic parts of the plate, so it's not the world's worst example. And again, I wanted to highlight here that this is an island arc, or a volcanic island arc, the kind of thing that Harry Hess would have been studying like in the 40s and 50s, and really came to understand, and that's why he's on the list of terms that you're supposed to be knowing from EVSC. Again, this is not easy to illustrate as I would like, because in the Google standalone app does a better job with the sub-ocean, the ocean floor features, whereas I have to admit the web app that I'm using right now, doesn't do that as well. Let's see if I can. Yeah, there we go. It doesn't show ocean the bottom features as well as the standalone app does, but you get the idea. There's this big trench that's forming down here as one plate is both plates are being pulled down by a slab pull type mechanism there. More exciting than that actually is the Mariana Trench. I'm actually going to search on Challenger Deep. The deepest place in the Earth's ocean is actually at Challenger Deep, which is part of the Mariana Trench in the there we go, in the Western Pacific. And again, we zoomed us in way too close. But you can tell we are in a really narrow, deep place in the ocean. Again, just very, very deep place here. Let's see, where are we at here? Again, I wish the animation of the ocean features is not as good on the web app, but you can get the idea here. Again, two plates are converging, and they're just both getting pulled down here along this boundary here. All right, that's all I needed to show you about that. We'll go back now to the PowerPoint presentation. All right, our third type of convergent plate boundaries are the continental to continental convergence here. And again, I ripped this diagram out of your book here. But these are where two continental plates or two continental crust plates are converging. And we'll learn more about all these different features like sutures and things like that, and the fragments and so on in a little, on a different day. But right now we're just getting the idea about what happens when these two continental plates converge with each other when they are capped with continental crusts. And it's actually going to be quite different than when an oceanic plate is involved, because oceanic lithosphere tends to be dense. It's basalt, contrast to the granitic rocks of the continental lithosphere. And since the ocean is more dense, it readily sinks into the mantle. But actually, granite floats on magma and the asthenospheric rocks and so on. It's going to actually be very hard to make any of this subduct. It would actually rather build up into the air in the form of mountains than be subducted down. And so, really the classic example that your book uses too is the Himalaya mountains. If you wound the clock back 10, 15, 20 million years ago, before India, the subcontinent of India had hit the Asian plate, there was actually a narrow ocean basin between India and Asia. But with time, as the Indian plate has continued, the Indian subcontinent has continued to advance to the north, it has been a continental to continental collision, and we have built up the Himalaya mountains. And in fact, the Himalaya mountains are still growing to this day. This is an active place where mountain building is happening. Now, chapter, I believe it is 7, later in this module, will be very much more detailed about what this kind of mountain building entails. But I'm just going to give you a little tour of 3 different mountain ranges real quick that are going to be created using continental convergent plate boundaries here. So let me just see if I can launch this one smoothly here. Okay, the next thing that we were supposed to be looking at here is some examples of where two continental plates are colliding. And so I'm going to show you some examples of mountain ranges that were created by that. And of course, the textbook example is the Himalaya Mountains. And if we go take a look real quick at that, let's see here. This is going to be where the plate that carries the Indian subcontinent was crashing into the Asian plate. And you can see here, again, it's such a big feature, but as you see how India was crashing into Asia, you get these very tall mountains, the tallest mountains in the world. Mount Everest is here. What other mountains are there? The K2 is the other really famous one here. Here, let's actually zoom in on some of these guys here. Let's go to Mount Everest just to say that we did it. Mount Everest. Let's just go to Mount Everest there. And I never know why. Sometimes Google Earth takes you to the wrong. There's apparently there are businesses called Mount Everest there, and some of them are not all that close to Mount Everest itself. So let's see here. Yeah, I mean, these are the tallest mountains in the world, and my network is having a hard time keeping up with all the refreshing and so on. But you can see these very, very high mountains that were brought up when those two continental plates were pushed up against each other. All right. I think on the list I said let's also look at the Alps, another good example of that. Let's go to the Alps. All right. All right, so we're going off to Central Europe here. All right, the Alps are these mountains that form. Let me back up just a second here. Italy is part of a continental plate that is pushing up into the Eurasian plate. And so along the northern end of it here, we're getting these very high mountains here. And I mean, again, depending on how familiar you are with the geography of that region and so on, these guys are really high mountains. Let's just see here. Let's just zoom in a little bit here. Let's see what we can find in a nice 3D view here. Yeah, these are nice tall mountains here. Let's go to 3D that are being formed as those two continental plates are pushing up against each other. The third one I wanted to have as an example was the Urals, which may not be as familiar. These are in Russia. And to be honest, I didn't preview this one on Google Earth, so I'm not entirely sure what feature it's going to, in the Ural Mountains, it's going to take you to. But again, this is a boundary where two continental plates collided. And it's it's kind of the boundary between what we consider Europe and what we consider to be Asia. And let's see if we can just get a good example of some mountain features in the Urals. How about over here? Let's see what we got here. Ooh, nice snow-covered mountains again. All right, and let's just zoom in a little closer and switch to 3D perspective. And you can see, oh, the nice little ridge of mountains here where those two plates collided with each other. All right, well, that's what we need there, and we'll just transition back now to the PowerPoint presentation. All right, so all that has been about convergent plate boundaries. Let's talk real quick about the third possibility, which were the transform plate boundaries, which are going to be ones that are in section 4.6 in your textbook. We're going to be talking about the relative motion along a transform fault boundary, and we're going to talk about several examples of them on a map. Transform, okay, so far we talked about the divergent boundaries, where plates are spreading apart from each other. Like if we looked at this, zoomed in on this little place in the bottom of the ocean here, we could talk about this place here where this piece of oceanic crust was being pushed this way, and this one's being pushed this way, and this is a stretch here that is a divergent plate boundary. But and here's another divergent plate boundary, but in between, there's this place where this part of the plate is moving this way, and this part is moving the other, and these are transform plate boundaries, where the plate is sliding past each other. And to be honest, most of this is under the ocean. Now, that doesn't mean it's unimportant. I mean, earthquakes that happen under the ocean are actually quite important. They trigger tsunamis and things like that. But, you know, that isn't the ones that make all the real news here. Clearly, when we are excited about transform faults, we're going to be talking about the ones that trigger earthquakes, especially in places like California. The San Andreas Fault in California is a large transform plate boundary, as the Pacific plate is headed off to the north and west, and North America is slipping relatively far to the south and east. And along that stretch of the fault, there are going to be multiple, well, we're going to learn in chapter 6, I think it is earthquakes, we're going to learn that the San Andreas Fault is actually a very complicated place, but it even has surface manifestations where you can actually see the crack itself in the ground where one side of this line is Pacific plate and the other side of this line is North American plate. So transform faults are kind of the ones that we end up spending a ton of time on when we do earthquakes, so we don't need to get just too bogged down with them at this time. Now, at this point in the book, they switch to a section 4.7 that's about how do these plate boundaries change, and the book throws up some definitions about talking about why it is the African plate and the Antarctic plate, are they changing in size, and the Pacific plate, why is it changing in size? But we're actually not going to worry about that. I'll make sure that nothing about that shows up on the test. Because the more interesting thing that EVSC throws at us about 4.7 is they want to make sure we talk about the supercontinent of Pangaea. I think people in general have this vague idea that once upon a time, all the continents, they were moving around due to continental drift or plate tectonics, and there was a time when they were all connected as well. And that is Pangaea. Well, the idea of Pangaea, which was part of what Alfred Wegener really was discovering when he was coming up with this whole idea of continental drift, well, Pangaea is actually only the most recent example of a supercontinent. I mean, recent is a difficult choice of words when you're talking about something that happened 335 to 175 million years ago, but it is by far the most recent of the different times on Earth when we have had a supercontinent. In fact, if we made a timeline of all of Earth's history going back, about 4.5 billion years ago, well, actually Pangaea is only that little piece that I have colored there right near the end, near the present. By the way, all of life is actually fairly near at least multicellular. The Phanerozoic, the part of the Earth's history that is easily revealed by fossils, is only this last little bit, the last 500 million years or so. So of the 4.5 billion years of history, only the last 500 million there's like readily available fossils. It isn't that there weren't, single cell creatures and little slimy things that didn't have shells and stuff like that earlier. They just don't leave fossils very readily. So Pangaea is the most recent time in, example of a supercontinent, but there have been at least 3 and possibly as many as 7 or 8 times in the past where the continents had moved around. I mean, frankly, Earth's history is long. We've got 4.5 billion years of moving the crust plates around. We've had plenty of time for them to collide and so on. And so at least 3 other times we've had supercontinents as well. Now, your book actually, splits this down to give you this idea here. They actually really disassemble the idea that 200 million years ago, all of the plates came together and they were forming Pangaea, and then rifting separated North America from Eurasia and started developing the Atlantic Ocean, and then South America started splitting away from Africa, and that extended up here to make more Atlantic Ocean, and so on. I don't really want to get into all that detail, though. I think that a lot of this is difficult to reconstruct, and I think just the idea is more important. That, as these plates move around, picture, so a couple things are floating around in the bathtub or something like that. A bathtub, you got a couple of toys floating around. I don't know, I have little kids, I think about toys being in the bathtub. Well, sometimes they're very far apart in the tub, and sometimes they've drifted and they're kind of all in a clump, and the same is true of continents, okay? Sometimes they drift into each other and they form a clump that is a supercontinent, be that Pangaea most recently, or any of the ones before it, like Rodinia and so on, or they've drifted different directions, like we currently are. Right now, the continents are about as far apart as they can get. If we look into the near future, near again being a hard word to use when you're only talking 50 million years in the future, North America is going to lose California. Okay, California is headed off toward Alaska. In merely about 10 years, Los Angeles will pass by the current location of San Francisco, and it's not going to stop. It's just going to keep going up towards where Alaska is, and so on. You can see within 50 million years, the Mediterranean is gone as Africa continues to tear off to the north. I don't even know where they're thinking East Africa went in this picture, and so on. But the book even takes it farther than that, even went out to like 200 million years and so on. But clearly, we don't necessarily know all the forces and how they'll change, as to where all the different forces that are acting on the Earth, moving the plates around on that kind of time scale. But there have been supercontinents in the past, and there will be supercontinents in the future. It's just right now we happen to live where there are several distinct continental plates. From there on out, the book has 3 more sections, 4.8, 4.9, and 4.10. And 4.9, well, 4.9 is sort of like applying the scientific method to plate tectonics and talking about like what kind of evidence do we have and stuff like that, and how do we test it and so on. And I think it would be more important to just talk about a few specific things. In particular, when I look at the list of topics in this section of the book that EVSC was concerned about, there's 1 or 2 here that we haven't hit yet, and in particular, paleomagnetism. Okay, paleomagnetism is a type of evidence that we use to support plate tectonics. We can't really watch plate tectonics happen. I mean, we can see some of the effects of it and so on, but it's not something we can really readily observe. So we need to have some way of finding evidence that this has happened in the past. In the past, or ancient, is our use of how we get to this word paleo. Paleo is like when we're studying something that, or examining something that happened in the past. In this case, we're going to be talking about the past magnetic field of the Earth. Later in the course, we'll talk about paleoclimate, studying the climate of the past and so on. Well, we're going to be seeing that, in fact, the Earth's magnetic field changes, and for that matter, the continents, as they move, they experience different magnetic fields. And as they move through these different magnetic fields, certain rocks, especially basaltic rocks, are going to be containing the mineral magnetite, and they're going to record these changes, and that could be evidence that we use to discover plate tectonics and describe it and so on. How does this actually work? When basaltic rocks are hotter than about 1100 degrees Fahrenheit, the number is not important. Hotter than that, one of the minerals that's in the basalt, magnetite, it doesn't happen to be magnetic. But when magnetite gets cooler than about that 1100 degrees, the magnetite crystals become magnetic, and because the material around them is still liquid, they can arrange themselves in such a way that they align the little magnets with the current direction of the Earth's magnetic field. Much like a compass needle in a compass can turn itself in the liquid that is inside the compass so that its little magnet is aligned with the Earth's magnetic field, a magnetite crystal can do that too. Now imagine if you took your little pocket compass and you froze it. Okay, now the needle is stuck pointing in a particular direction, and in fact, if you move the needle in different ways, if you move your compass in different directions, it can't turn anymore. it has kind of frozen or recorded what direction it was pointing when the compass froze. And in the same sort of way, if a basalt formation freezes, if it becomes less than 1100 degrees Fahrenheit or whatever the number is, it then, the magnetite will align itself along the direction of the magnetic field at that time and then freeze. And if the rock moves, well, it'll be pointing the magnetic, the field lines will point, the magnetite crystals are pointing the wrong way, but we can use that as a record of, but we know they used to point the other way. Okay, so these crystals are now pointing the wrong direction. They give us a way of understanding, oh, the Earth's magnetic field, we've either moved the rock or the Earth's magnetic field has turned. So we can do this, and in fact, probably the easiest way to see it is where there's seafloor spreading going around. So remember, these are going to be our freshest rocks. And then as they get older and older, they're getting pushed away due to the seafloor spreading. And we can take a research vessel that tows like a magnetometer and pull it across here. And as we go, we record places where the magnetic field is, well, they actually do it in terms of normal, as in the magnetic field is in the same direction. Those rocks are pointing the way they would be pointing if they formed now. Or this white color is the opposite direction. Wait a minute, why are there these bands like this? Why are there periods of time where the magnetic field seems to be wrong? Well, as you possibly know, the Earth's magnetic field does change with time, and in fact, every few 100,000 years, it reverses. So if I just go back a slide here then, we see periods of time where the magnetic field, the rocks are recording a magnetic field like we have now, but then there are periods of time, which they labeled in white here, where the rocks show the wrong magnetic field. They're pointing the wrong direction. Well, that's just because that magnetic field was such that the North Pole was at the south. We aren't going to get all bogged down as to why the magnetic field reverses and so on, but this is recording that there were times when the magnetic field went the other way, and for that matter, we can use the dates of that to figure out how old these rocks are and so on. And like this shows us an example here. This is off the coast of western United States, where research vessels have found all these magnetic reversals and all. We can see all the different ways in which the plates have moved over time. This also can be used to show the wandering of the magnetic poles. The Earth's magnetic pole drifts a little bit. It's not exactly the same thing as the North Pole of the Earth, and we can use paleomagnetism to record that. We can record how the plate itself moved and so on. Paleomagnetism is an important tool to reveal and provide evidence for plate tectonics. So finally, just to wrap up with this very long lecture here, why are these plates moving? What actually brings this all about? And I kind of haven't entirely told you the whole truth yet. I mean, we often talked about the fact that like the magma, or maybe even we could say the asthenosphere, underneath the lithosphere is moving and it can drag the plates with us. And that can be part of the story. We would say that that is an example of convection. Now, convection is a broader idea than that, but broadly this idea that like there'll be places, well, like here's a big kettle on the stove. When warm water at the bottom rises and cooler water on the edges of the pot sink, that's an example of convection. Where warmer fluid rises and cooler fluid sinks, that is a broad idea of what convection is. And so one way to think about the whole idea about plates moving is maybe there's convection going on in the asthenosphere, and like warm material is rising, and then as it spreads out and sinks, it's dragging continental plates with it. But that's actually not really the tool the book wants you to have right now. It wants you to think more specifically about ideas like slab pull and ridge push. We're going to switch over here to this diagram here, where here we have some seafloor spreading right here, and we have a mid-ocean ridge. And then there's ocean plate, it's getting cooler, it's getting more dense, it's getting cooler, and then at some point it hits a trench and it's getting pulled down. Okay. As this plate is getting pulled down, it's cold, this is old, heavy stuff. As it starts pulling down, well, just gravity starts pulling this slab down into the relatively light asthenosphere. So this is getting dragged down, and it's just pulling the whole ocean plates with it. Here's how I would like to think about it. Picture like a tablecloth, okay? The ocean plate is like a tablecloth right here. And as you take, as a little kid, you might have grabbed the tablecloth under the table and you start pulling. All this stuff is just getting pulled and pulled and pulled and pulled until it goes off the edge of the table. And it's going down, down, down now. Okay? That's slab pull. The weight of the tablecloth just pulling the tablecloth off the table with you. Okay, I actually meant to shoot a video where I was demonstrating this, but you know what I'm talking about, right? The tablecloth just sort of sliding off because the weight of the tablecloth is pulling it off the edge of the table. All right, that's slab pull. But while we're at it here, we could also talk about ridge push, which is a secondary process that's happening here, which is just a matter of, remember, as this mid-ocean ridge is forming and it's physically higher than the ocean basin around it, the gravity as it pulls it down, it sort of slide, the material has a direction of force that's pulling it, pushing it down along the plate boundary here. And so these mountains that are forming under the ocean in the mid-oceanic ridge are pushing the material toward the trench too. So this is sort of your number 2 phenomenon, whereas number 1 is slab pull. And slab pull would really explain like why ocean plates do this, where they spread out in the middle and then they get older and older as they get closer to the edge of the trench, and then as they go down into the trench, the weight of the plate itself is pulling the material into the trench. All right, that actually brings us to the end of chapter 4, which is the first chapter of this module of the course. The rest of the module is all about the consequences of plate tectonics, things like volcanoes and earthquakes and mountain building. All right, well, that was almost an hour long, and that makes a good online lecture. Please let me know if you have any questions about this. This has been Dr. John Schrage.